All right, let's get going. It's 10 o'clock and it's time for another warm, sunny morning of chemistry, Chem 1211, with your host, me, Dr. White. Good news, I survived my vaccine shot. Actually, where I got it, the medical practice I belong to is called NCH Group, Northwest Community Hospital, and associated things. And they had their own vaccine clinic, which last Friday I was finally able to get an appointment for Monday afternoon. And those guys are amazing. It was well run. I was in and out of there. They're very professional, very polite, very nice, which people at NCH always are, and very little problem. And on April, a couple of weeks, I'll go back for shot number two. All right, important announcements. One, today, right after class by 12:15 at the latest, I will be sending out individual emails to all of you with the password for your version of test number two. You have until 1 p.m. tomorrow to take the test and upload it to Blackboard as a single PDF file. On the test, it will say underneath your name, like you see in test one, please use proper significant figures for all calculated answers. And under that, it will also now say, please use three significant figures for all atomic weights. Now, uh, first of all, uh, make sure you check your test before you upload it, the PDF file. Make sure you have all the pages for answers in there. I've had people in labs and stuff forget a page, so don't you. I promise by Sunday, 1 p.m., probably a lot earlier, I will have one, your score for test number two in Blackboard. Two, I will individually email each one of you with the points for each answer you put down in test number two. All right, next announcement. I've mentioned this before. Starting this Thursday and Friday, your lab, if you don't get it in by Sunday, 1 p.m., you're going to get zero unless there's some very extenuating circumstances. Uh, it's a robocall. Two more rings. They gave up. But anyways, I don't know about you, but I screen all my calls because there's a lot of garbage coming through. Anyways, don't forget for the labs, get them in on time. Uh, Please, you don't want to lose easy points. Labs aren't that hard. One other thing, the lab that you'll do this to Thursday and Friday will not be due next week because next week is spring break. And I'll say it tomorrow for Thursday's lab and Friday for Friday's lab, but I figure I'll do it for all of you right now. Everybody, if you celebrate it, have a happy Passover. I've already made my matzo balls. They're in the freezer ready to go for Passover. And if you celebrate Easter, have a happy Easter. Hopefully you get all your little chocolate bunnies you want. And for those of you who celebrate neither Easter or Passover, I hope you have a happy spring break and celebrate whatever you want to celebrate. And with that, I thought I'd mention it. Now, next week, there'll be no class, but as a special thing for you, if you need some extra help over spring break, I will be here for my office hours on Monday and Wednesday night. So if you need some extra help, stop by, say hello to Dr. White. By the way, if you're going out of town or somewhere special over spring break, don't forget to send Dr. White an email saying, having a great time, wish you were here. Or you can send me an email, having a great time, glad you're not here. Uh, Let me tell you a little history of that. When I worked in the 80s and 90s for two Dutch companies, I went to Europe a lot. and I'd be there for a couple of weeks at a crack. And I'd go to a number of cities such as Amsterdam, Brussels, London, Manchester, Liverpool, and a few others in the Netherlands, Den Haag, The Hague. And every time I go to a new city, I go to a local gift shop. I had a long list of relatives, my close relative, my sister, my mother, and other relatives, my friends, and also people who worked for me in my research group. I think it was about 30 people. I go get 30 postcards, and one city I'd write, having a great time, wish you were here. And next city I'd write, having a great time, I'm glad you're not here. And I'd mail them back, and people always enjoyed getting those postcards. All right, before I start, don't forget, at 12:15 or earlier, I will be sending out the email with the password for your version of the test I want you to take. They're in the assignment area of Blackboard. I almost said the other school system, D2L, and you can download it. One other thing, today about every 2 hours until 9 o'clock. Oh, don't forget, I'll have my office hour tonight. If you have any questions, email me or come to my office hour. And tomorrow morning, I'll check early too, like I always do. All right, any questions before I proceed? Look at the chat. All right, let's get back to material that will be on test number 3, but I do have to go over it now, which I do. Those of you who have your webcam on, thank you. So I get to see real faces out there. Thank you, real faces. And I appreciate it. All right. Yesterday. Yesterday was an interesting day. Well, anyways, I talked about on Monday the ideal gas law. The ideal gas law. Oops, let me do something real quick. That way you won't see all the proofing markings. Microsoft Word and chemistry don't get along well together. And let's do it. All right, the ideal gas law, PV equals nRT. P is the pressure, and it has to always is in atmospheres, no other units. V is the volume in liters. I'll always give you volume in liters. You can convert from milliliters to liters. I'm not going to make you do that. N is the number of moles. And I've never seen a balance or way of measuring mass or moles, but you measure grams. And hopefully for test 2 and also for this type of problem, you know how to go from moles to grams and grams to moles. And finally, temperature, T is in Kelvin. And I've never seen a thermometer in Kelvin. And by the way, all this on this page right here, I will give you important information. Test number 3, as I've mentioned all semester, about almost 2 years ago now, I came to the philosophical conclusion that, oh, that's a big word, philosophical, that I should test your knowledge of chemistry, not your memory. And therefore, I don't make students memorize this anymore. And finally, R is the universal gas law constant. For my class, I'm using the number, there are different values of R, depending on the units. I will always use 0.0821 atmospheres liters per mole Kelvin. And this will also be given to you. Now, as I mentioned on Monday, remember that, let's go to whiteboard. Thumbs up, people. You see a blank whiteboard? Thank you. In winter, you should check your car tires. Why? Because the temperature goes way down in Chicagoland. And we have PV equal nRT. In your car tires, V stays constant, unless you get a flat, and then it doesn't matter about the temperature. Hopefully you don't. N, number of moles stay constant, and R is the universal gas law constant. So PV equal nRT is a law and is always true, and it is. When the temperature goes down, the pressure goes down. So you should check your car tires. In summer, just the opposite happens. If you were here in the summer at 895, temperature went way, way up and stayed there for a whole 2 weeks. And what I saw on a toll road were a lot of cars and trucks pulled over with blowouts. Why did that happen? Well, they didn't know PV equal nRT. And because of that, in the summer, the temperature goes way up. This N, R, and V stay constant, but the temperature changes. And the only thing on this side that can change is the pressure. Temperature goes up, the pressure in your tires goes up. And eventually, if you didn't check them, it can go boom, blowout. And that happens. I'd like this morning to do 2 more PV equal nRT problems. And what I'm going to do, because it's really not practical to ask you to do the whole thing at one time, I'm going to do some steps. That reminds me. Did I ever tell you about Winky Dink? Did I talk? I did. Oh my goodness. Bad Dr. White. Well, I was about 6 or 7. A real popular TV cartoon show on Saturday morning was, and I was addicted to cartoons. My friends were too. They're a lot better than the stuff they have on now, which is real wimpy. But anyways, they had this one show called Winky Dink. And Winky Dink had a hair like stars, like a star, real spiky. And he had a sidekick who I can't remember his name right now. I want to say it was Tag, a tiger, but don't quote me on that. But anyways, what you did was you sent them the phenomenal amount of money, 25 cents, and they sent back to you a piece of plastic that you put on your TV screen and a grease marker pencil. And during the show, you'd have where it said, "Oh, kids, Winky Dink is stuck in the hold of the ship. Draw on the ladder so he can get out." And they'd show a dotted line. You go up to the TV screen with the plastic on it and draw your ladder, and you'd see him climb up your ladder. And you wipe it off, and I'm going to do a Winky Dink on you. I'm going to do, help me out, do this and that. By the way, I remember my best friend at the time, Dickie Gale. He was about my age. He forgot to put the plastic on the TV. Oh, did he catch it from his parents? So if you ever do Winky Dink, don't forget to put the plastic on your TV. True story. All my stories are true. All right, let's do it. Uh-oh. Thank you, Danny. You're right. Everybody see my white screen? I forgot to check. Thumbs up, people. Thank you. All right. If a balloon has 3.52 grams of oxygen at 749 torr and 26 degrees C, then what is the volume of the gas in the balloon? All right, first of all, we're going to do Winky Dink time. Everybody over here, right here, write down what are you being asked to find And what are you given? All right, I think everybody's done. Let's do it. All right, what are you being asked to find? What is the volume? What are you given? You're given, you have 3.52 grams of oxygen. You're given a pressure, 749 torr, and you're given a temperature, 26 degrees C. Now, this is a mass, which you can always go to moles. This is a pressure. This is a temperature. And one other thing, oxygen is a gas, which it says also right here. As soon as you see that plus hint, hint, wink, wink, say no more, you should think about PV equal nRT, where P is the pressure in atmospheres, and this you'll be given. V is the volume in liters. N equals the moles. And for today's test, I hope you know how to go from grams to moles and back again. And next, R is the universal gas law constant. And T is the temperature in Kelvin. And I think I'm being Italian today because I look like I'm writing on the Leaning Tower of Pisa. But anyways, this is PV equal nRT. Now, time again for you to help out Dr. White, who's not winky-dink, but right here, write the equation you would use to calculate V. In other words, take this and solve for V. Just with the letters, no numbers. I'm gonna work you hard today. Where's my whip? Oh yeah, you gotta buy a new one. If my humor gets really strange, I can blame it on the vaccine. Not really. It's always been real strange. I guess that makes me Dr. Strange. No, I'm not a magician. I'm really going far out with Marvel comic jokes. All right. Thumbs up, people. Has everybody finished with that? And the answer is, I think so. So let me help you out. How do you solve for V? I'm going to show you the steps. You don't have to show each step, but I do so you can see. I want V alone on one side. Well, how do I get rid of P? Well, anything divided by itself equals the number 1. So if I divide this side, because you're multiplying here, by P, it will cancel out and I'll be left with V. But whatever I do to one side, I have to do to the other. And therefore, what is V equal to? V is equal to nRT divided by P. Now, remember, each of these variables, N, R, and T, and P, R is already given to you, so you don't have to worry about it, but N, and in this case, pressure and temperature, have to be in the right units, which they're not. Remember, pressure has to be in atmospheres. N is moles, and T is temperature in Kelvin. Common mistake on test number 3, students don't convert the units for the various variables to the correct units. Now, on test number 3, I will provide the following. Two days later, I'll be finished, but I'm almost done. All right, I'll provide to you 760 millimeters of mercury equals 760 torr equal 1 atmosphere. I'll also provide to you Kelvin equals degrees C plus 273. In both of these, 760 and 1 are exact numbers. 273 is an exact number. I'll also provide to you 1 mole of a compound equals the molecular weight of a compound, and molecular weight of a compound equals the sum of all atomic weights. So we got to get to work. Let's get to work. Find N. So if we look up here, we have 3.52 grams of oxygen gas, O2. The atomic weight of oxygen, the 3 significant figures, which you know how to look up on a periodic table, is 16.0. Why don't you now, it's going to be winky dink time again. Kids, help Dr. White out. Convert 3.52 grams of oxygen to moles of oxygen. Go. Don't forget to use your good buddy, your good friend, unit analysis. I love that. Oh, it makes my heart feel so good to see everybody out there doing their chemistry and using unit analysis. Thank you. And the votes are coming in. And it looks like everybody's just about done. So I'm going to go ahead with this. And the question is, we want to convert this to moles of O2, oxygen gas. And now I'm going to use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top the units. Whatever I'm trying to get rid of go underneath. This is moles of O2. This is grams of O2. Where do I get that number? Right up here. 1 mole of a compound equals the molecular weight. The molecular weight of oxygen is 2 times 2 oxygen, 2 times 16.0. That's 32.0 grams. So 1 mole is 32.0, did I say 6? 32.0 grams. And now I remember this is 3 significant. This is the exact number. This is 3 significant, the 32.0. This is a multiple step calculation. Therefore, you can either round off at the end or you can do it at each step. And I'll calculate both ways, even though Dr. White is a round off at each step person. Oops, I got to open up something I forgot to open up. Huh. Uh-oh. There we go. And the number you get is 0.220. Wow, I just picked a number randomly when I start doing this problem, and I picked that. So is the 3 significant figures 0.220.
Professor,
Yes,
isn't it 11? Because
what did I do?
you divided by 16 is supposed to be 32.
That's right, thank you. Well, I appreciate your help. As I said, I'll make a mistake, and I just did. I'm going home. I am home. All right, let's get back to work. Keep an eye on me. Must be the virus vaccine. Nah, I can't blame it on that. And now here we have 0.110 moles of oxygen. All right, what's next? We got N. R, we're already given. That's the universal gas law constant. What's temperature? Well, come down here. Temperature in Kelvin equals degrees C plus 273. And for this problem, let me check so I don't make a mistake. It's 26 degrees C plus 273 equal 299 Kelvin. Let me check my math. And remember, this is an addition. This is an exact number, and you get the same number of significant figures to the right of the decimal as the number has the fewest. This has 0, which is why this has 0 past the decimal. All right, we've got N, we've got R, we got T, we got to do P. And this is a common mistake. Students put this value in. No, pressure has to be in atmospheres. So now I'll go and say I have 749 torr. And what do I want to get to? Atmosphere. So it's time once again for you to help out Dr. White. What goes on top here and what goes underneath here? Use your good buddy unit analysis, good friend. And remember, 760 millimeters of mercury equals 760 torr equal 1 atmosphere. Your turn. Help Dr. White out. I need it today. I'm just getting something set up on the spreadsheet. All right, time's up. Put down your pen or pencil. How do you proceed? Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of this ratio. Whatever we're trying to get rid of goes underneath. Where do we get these numbers? From the fact that 760 torr equal 1 atmosphere, and therefore I can write in atmosphere on top, torr underneath, and 1 atmosphere is 760. These are both exact numbers. Therefore, this is 3 significant. My answer should be. So now I'll go to my calculator. Keep an eye on me. And I'm going to round this off to 3 significant figures. I'll let you do that first. You don't have to, but I will. Keep the 9, keep the 8, keep the 5, use the 5 to round off. That's 5 or higher. Therefore, I'm going to drop this, increase that by 1, and this would be in here 0.986. And now what I'm going to do is, now that I've calculated everything, I can say volume equals what's N? Well, that's 0.110 moles. What's R? And that's up here, and it'll be given to you 0.0821 atmospheres liters moles degree K. And temperature is right here, 299. And then what's my pressure in atmospheres? It was, I forgot to write it. Let me check. 0.986. And so I'll put it here. Now, since I had to write it so small here, I'm going to write down here the units above. I have moles times atmospheres liter per mole Kelvin times Kelvin divided by atmospheres. Now, if we forget about this part, moles divided by moles cancel out. Kelvin divided by Kelvin, remember this is a ratio there underneath, cancel out. Up here, I'm left now with atmospheres liters. Atmospheres divided by atmospheres cancel out, and I'm left with the units I want, liters, which is volume. So what is this equal to? Let's go do the math. And for a spreadsheet, I find it works better, quicker if I do it in 2 steps. And if we round it off, oh no, I've done it again. I'm on a winning streak. Then either one round off to 3 significant figures. I'll let you do it first. Time's up. Both of these, keep the 2, keep the 7, keep the 3 in column F. Is that 5 or more, 4 or less? It's 5 or more. Drop all that, 2.74. Same thing here, keep 2, keep 7, keep the 3. The 9, is that 5 or more, 4 or less? I hope you said 5 or more. Drop that, the 3 becomes a 4. And therefore, we get 2.74 liters is the amount of the volume of the balloon. If you think about that, that's almost 1.5 2-liter bottle size of pop, but it's a gas, not a liquid. And that's how you do PV equal nRT. You know something? Let's do another one. And this one, I'm not going to do winky dink because I want to show you something. I'll do Dr. White does it totally. And let's look at the problem. All right, let me decode this for you. And the question is, if a car tire has 9.87 liters, that's what L is, liters of nitrogen gas, N2, you should know that's nitrogen gas, at 25 degrees C, 1.65 times 10 to the third torr, then what is the weight in grams of the nitrogen in the tire? Oh, what do I do? Well, first of all, what am I being asked to find? Grams of nitrogen. What am I given? A volume. 9.87 liters nitrogen gas. I'm given a temperature of 25 degrees C and a pressure of 1.65 times 10 to the third torr. And I look at this and I say, well, it's a gas and nothing is changing. So it must be PV equal nRT. But wait, I'm being asked to find grams. Oh, I remember. Remember, you can convert, and hopefully you know it for today's test, moles to grams. So how do you do this problem to get the moles, grams of nitrogen? You need 2 steps. You solve the PV equal nRT for N, which is moles. And step number 2, go from moles to grams, which you should know how to do already. So let's get to work. What do I want to do in step 1? Solve PV equal nRT for N. Well, how do you do that? Well, if I want N alone, I've got to get rid of R and T. Well, since this is all multiplied, I can divide by those. I'll divide this side by RT, and that will cancel out, and I'll have N. But whatever you do to one side, you should do to the other. So now I'm left with N equal PV over RT. And Dr. White's going to rewrite it because he likes to do that. And good habits I don't change. So now we have to solve for N. And as you learn, you have to have P in atmospheres. So let's do that. But we're not given P in atmospheres. We're given it in torr. And remember, 1 torr, 760 torr equal 1 atmosphere. So I can start like this. And I'll use my good buddy, my good friend, unit analysis. Wherever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And I'll write those in right now. And where do I get that? Way up here, 760 torr equal 1 atmosphere. And there we go. Remember, torr divided by torr cancels out. Then I'm left with atmospheres. Remember, 760 and 1 are exact numbers. So this is 3 significant. My answer should be 3. No, actually, I can do this over here. And I get 2.17, which I'll convert to 3 significant figures. And that's my pressure. So I'll come over here and say my pressure is 2.17 atmospheres. I'll write it down here. All right, that's my pressure. My volume, oh, Dr. White was nice. He gave it to us in liters, and that's equal to 9.87 liters. So I'm done with volume. R, which you'll be given, is the universal gas law constant, 0.0821 atmospheres liter per mole Kelvin. And finally, temperature, which is in Kelvin, which we need right there, is degrees C plus 273. And degrees C, if you look up here, we took the time to figure out, is 25. Plus 273 equals 298 Kelvin. And now, I'll go to my spreadsheet and I'll put in the volume was 9.87. Next, R, 0.0821. And finally, let's go back. The temperature, if you look at, was 298. And now what I'll do is take PV, my pressure, times my volume, that's the top, and I'll multiply and get that number. And I'll get that, which I won't round off this. I could have possibly, but, and then, because this you can do all at once in a calculator, I'm just doing it stepwise. Then at the bottom, I have divided by R times temperature T. And then I'll get my final answer, this divided by this, and that's what I get. All right, finally, I have a difference. If you look at column E, round that off to 3 significant figures, that'd be 0.876 grams of N2. And if you look at F, you have 0.875 grams, which is the right answer. On my test, either one, because I don't make you, well, we're not done yet, but I don't make you round off. So at this point, N is equal to either 0.876 grams of nitrogen. Oh, wait, not grams. Bad, Dr. White. Moles of nitrogen, or 0.875 grams of nitrogen. Now, I'm going to go a couple minutes over into our break because I want to do step 2. I've used this semester. That's how in my notes I'd write a break, something different when I was in college. Step 2, moles N2, 2 grams of nitrogen. I have, let's go with the 0.75, but I'll do this for both calculations. Moles N2. I want to get to grams of nitrogen. I see a comment. Kelly, did you get a different answer, Kelly?
No, I kind of lost you with the numbers we were calculating.
All right, I'll go back and do that.
Sorry.
We'll go a little past our normal break time, but I'm not going to cheat you out of your 5 minutes, or me either. All right, you see the numbers up here. This is pressure. This is volume. This is R. This is temperature. This is pressure. I found it's easier, quicker to do stepwise in a spreadsheet. It might be on a calculator too. This is this. This is R times temperature. And if you take this one and divide it by this one, then you get does that help, Kelly?
Yes.
Thank you for your question. As always, all questions are good questions. All right, let's get back to our problem so I can get you out of here before midnight. And if we look here, how do we get to grams from moles? We use our good buddy, our good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. I'll write that in. And where do I get these numbers? A relationship between moles and grams. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight in grams of that compound is the sum of all atomic weights in grams. So now, where are you? Over here. What I need right here is the molecular weight of nitrogen gas. And if you look over here, nitrogen gas has 2 nitrogens. If you look on your periodic table, the atomic weight for nitrogen is 14.0, and this equals 28.0. So for every 1 mole of nitrogen, I have 28.0 grams of nitrogen. And now I can go to my calculator, which this is really N. And I'm going to get over here now, grams. How am I going to do that? My moles times 28.0. Now, if I'd round this off to, which I tend to do, 8.75, and oh no, I pulled it off again. The 3 significant figures, you get the same answer, 24.5 grams. And so the answer to that problem, now I know why it's 15 points, should be even more, is 24.5 grams.
Now it's recording.
All right.
No recording, yes.
If you ever see us pause, let me know. This is the second time I did it. Monday, I did it near the very end. I went back and redid it alone, what I missed, but I don't know how much I missed right now, but let me know if you ever see where it doesn't say recording on there on your screen, say, Dr. White, you stopped recording, okay? I'm gonna have to write Zoom. They should move the recording, stop recording away from the shared screen. I don't know, put it all the way to the right or left, just away from things. All right.
It recorded in the beginning,
Oh, I know I
at
did
least in
for
the
a
class.
while, but then it just stopped because at the bottom of my screen, I have a green thing called shared. And it's right next to the button. I don't know if you can see this. Hold on, let me see if I can move it. If I go like this, hold on. When I go to shared screen, can everybody see in the middle of the screen that bar? Or is it only I can see it? Do you see a bar?
Yes.
What? Do you see,
Yes.
see where it says new share and pause next to it? Oh, I can see it. The pause and the share are right next to each other. If I'm not looking closely, I obviously have clicked the wrong button. All right, let's get back to, keep an eye on that for me, please. I'm gonna have to write Zoom about that. All right, let's move on. We've done our practice time and you've seen my board, so I better move on. Now, switches off for these next couple of slides, click. But I do want to mention it. There's something called molar mass, and that's the idea that a gas in an ideal gas law of weight, one can calculate the molar gas mass of a gas, how many moles it is, or weight per 1 mole. And that's that. All right, switches on, click. Another important law is Dalton's law of partial pressures. And the law is, and I'll show you, you don't have to write this down. I'll show you the equation. The total pressure exerted by a mixture, and that should be of gases, is the sum of the individual partial pressures of the individual gases. What's a partial pressure? Well, good news. First of all, I don't know why I have dots there. Hold on one second. There. The partial pressure of a gas is the pressure of that a gas in a mixture would exert if it were alone under the same conditions, temperature, pressure, and volume. So partial pressure is what, if you have a mixture of gases, what the pressure of each individual gas would be if it were alone. And therefore, Dalton's law of partial pressures is P total. The total pressure equals the sum of the partial pressures, P1, P2. This would be like nitrogen, oxygen, argon, whatever. And know this. Now, on test number 3, I will give you Dalton's law of partial pressures, but you have to know how to use this. So let's do some practice. Remember, keep an eye on the record button. If you don't see that, let me know. And let me decode this for all of you who haven't figured out my handwriting yet, which I know a couple of you need it. All right. What is the pressure of a mixture of Ar's argon and two nitrogen gases if the partial pressure of argon is 351 torr and the partial pressure of nitrogen is 201 torr? This one Dr. White's going to do, by the way, is 3 or 4 points. And what are we being asked to find? The total pressure. What are we given? The partial pressure of argon, this is how you write partial pressure in chemistry, is 351 torr. The partial pressure of nitrogen is 201 torr. And how do we proceed? We use Dalton's law of partial pressures, P total equal the sum of the partial pressures of all gases. In this case, it's P argon plus the partial pressure of nitrogen. Well, we figured that out. That's 351 torr plus 201 torr. And if I add those together, keep an eye on me, I've been making mistakes today, that's 552 torr. And that's how you do it. And this turns out to be an important concept when you're dealing with various things in chemistry, such as if you have a mixture of water vapor and oxygen and nitrogen, and you're trying to find out certain things about that mixture of those gases. I'm going to let you have some fun. All right, let me decode this for you. 3 points. What is the total pressure of a mixture of krypton and oxygen gases if the partial pressure of krypton is 701 torr and the partial pressure of oxygen is 101 torr? And I'm going to share the fun. Have fun. And in case you forgot, remember Dalton's law of partial pressures, the total pressure equals the sum of all partial pressures of the mixture of gas. All right, I think everybody's done. Let's do this. What are we being asked to find? P total. What are we given? Partial pressure of krypton equals 701 torr. And the partial pressure of oxygen is 101 torr. And since we're trying to find the total pressure and we're given partial pressures, I know to use Dalton's law, partial pressures, in this case, P total, is the sum of the partial pressures, in this case, P krypton, partial pressure of krypton, plus partial pressure of oxygen. Say that 5 times quickly. Don't. And that's 701 torr plus 101 torr. If I do my math correctly, 802 torr. And that's your answer. Oh, let's do one more. These are fun. All right, let me decode this. A mixture of oxygen, nitrogen, and this gas has a total pressure of 761 torr and a nitrogen partial pressure of 601 torr. Then what is the partial pressure of oxygen? Let me remind you, Dalton's law of partial pressures, P total equals the sum of all partial pressures in the gas mixture. Your turn. All right, I haven't done it today, so let's do thumbs up if you're done. I think everybody's thumbs up, so let's do this. All right, what are we being asked to find? partial pressure of oxygen. What are you given? P total, the total pressure of this mixture, is 761 torr. And the partial pressure of nitrogen is 601 torr. And because of Dalton's law of partial pressure, we know P total equals the partial pressure of nitrogen plus the partial pressure of oxygen. Now, what are we being asked to solve for? This. So how do I get rid of something when you're adding? Well, A minus A equals 0, and it cancels it out. So if I want to get rid of the nitrogen partial pressure, I'll subtract. Try not to get ahead of myself thinking and writing. And this would cancel it out, and I'll be left with that. But whatever you do to one side, you have to do to the other. So I'll subtract this. And what do I get? I get P total minus the partial pressure of nitrogen equals the partial pressure of oxygen. You don't have to do this, but I'll turn it around. So it looks like this. I have total pressure 761 torr, and that should be a 1, and minus 601 torr. Now here, be careful, I haven't talked about this, but subtraction, I think it's the only time we'll do subtraction this semester, is the same as addition. You get the same number of significant figures to the right of the decimal as the number that has the fewest. This is 0, this is 0. The answer would be 160 torr. Because not that this is only 2 significant figures, but this has only 0 significant figures to the right of the decimal. And that's how you do it. Now, where do you, and I'm going to turn the switch off for the next slide or two. Where do you use this? A lot of times we have, and we'll be doing this in a lab this Thursday or Friday, when you collect a gas over water, when gas is collected by displacing water, part of the gas collected is the water vapor from the water. And you use Dalton's law of partial pressures and the ideal gas law, and one can calculate the dry pressure. Total pressure equals gas plus water. Pressure, partial pressure, water vapor. Therefore, gas pressure equals total pressure minus water pressure. And this is used to calculate certain masses. We'll see that later on. All right, switch is still off. There's something called STP. STP stands for standard temperature and pressure. And that's defined 273 Kelvin, 0 degrees Celsius, 32 degrees Fahrenheit, and 1 atmosphere. And someone real famous, Avogadro, determined at STP, standard temperature and pressure, 1 mole of a gas always equals 22.4 liters. Switches off for the slide. And this is why Avogadro's number was named after him, to talk about moles, because he was the first one to show a relationship of moles of something to an actual measurement. In this case, the volume. And you know what that means? It's the end of a chapter. Now, no, I'm not done for today yet. I had a class whenever it says You know what that means? They'd all close their notebooks and be ready to leave. And I said, wait a second, I'm not done. All right. First of all, remember, I still have more stuff I got to do today with you people. So don't run away or walk away or shut me off. And first of all, don't forget about by 12:30 or 12:15, or maybe even a little earlier, I'll be sending out emails with the password for test number 2. You have until tomorrow, 1 p.m. to upload it as a single PDF file to Blackboard. By Sunday or earlier, I should get all the scores in Blackboard. You should get an email with your individual points for each answer you put down on the test. Now, as a special service to you, I'm going to stick around a couple minutes after class, after class today. If you have a last minute question, ask. I'll stick around for a while, a couple minutes. All right, guess what time it is? It's new chapter time. And new chapter times are always exciting times because I get to talk about new stuff. For you, I've learned, but it's still fun for Dr. White. What's this new stuff? Well, we've talked about solids, like with gases, weights and everything. We just talked about gases. So let's talk about something to deal with liquids, and that's solutions. And solutions play an important part in our daily life. Everybody, when you just inhaled, the air you inhaled was a solution. I only have a little left. Hold on. I'll go on. What was in my mug, the tea, is a solution. By the way, if you notice, I have personalized mugs. And if you had some pop last night, remember Dr. White is from the Chicagoland area, and that stuff in a can or a bottle that's carbonated and very sweet and tastes good, like Dr. Pepper Werner's, is a solution. Ooh, one more. How many of you have driven by a gas station and think about the gasoline they're selling you is a solution? Wow, chemistry is all around you. Like right here, the air I'm feeling when I go like this, that's a solution. What are solutions? Good question. A solution, and I'll never ask you what is the definition of a solution, but I will ask you, thumbs up people, can you see it on your screen? Thank you. All right, a solution is a homogeneous combination of 2 or more substances in which each substance retains its own chemical identity. Ooh, big fancy word. Homogeneous. That means it's the same throughout. And you have a combination of 2 or more substances in which each substance retains its own chemical identity. Let's talk about that for a second. Now, I just realized how I shut it off. The stop share button is right under the stop recording button. That's a stupid place to put it. But anyways, let's assume I have some water and I put in some salt or sugar. If you wanted salty or sugar, if you celebrate Passover, you're going to be making some salt water, but look it up on Google. But anyways, if you go like this and shake it up, you look at it, if there was salt or sugar in here with the water, it would be the same throughout. That's homogeneous. Now, if I were to able to remove all the water or all the salt and sugar, both are still there as separate molecules. The water is still H2O, it hasn't changed. The sugar or sodium chloride, remember, pastanacal, NaCl, never mind. But anyways, that's still, if I took all the water out, you see all the sugar or water, salt molecules still there. And that's because when you make a solution, which is a mixture of 2 different or more substances, none of the substances are changed to react with each other. They don't lose their chemical identity. So as you inhale, don't forget to exhale, but as you inhale, The air around you is a solution. It's a mixture of oxygen and nitrogen. There are a few other minor things too. And each one is individual molecule that doesn't change. Same thing with gasoline. Gasoline is an extremely complex solution. Now, let's think about other solutions we have in our daily life. I don't know, what would be a good solution? I already said Dr. Pepper. Well, if you go to a local supermarket or liquor store and you get a good bottle of vodka, and what is vodka? Dr. White loves his vodka in Canadian Club. It's ethanol, a certain molecule with water and a few other minor things in there. And if you pick up a bottle of vodka, you'll see it's the same throughout. It's not different. Now, what wouldn't be a solution? And I'll talk about that. If you take, and we talked about that, if I were to take and put sand in here, I won't, but if I did, and I shook it all up, the sand would go right to the bottom. This would no longer be homogeneous. So a mixture of water and sand is not a solution. So think about daily solutions that are in your daily life. Kelly, different brands of what? You can turn on your mic too if you'd like to, or you can type it. Oh, well.
Just alcohol in general, like there's really
Right.
bad alcohol.
It matters how they distill it. This is I got a minute. If you're an organic chemist and an industrial organic chemist, when you do what's called a distillation, that's a purification of mixture. How well you do your distillation, how pure you make the mixture affects what you make. And if they don't do a good job of distilling, that's one thing. The other thing that makes vodka taste different is what it's made from. There are two main different types of vodka, and the best kind, if you're from Russia or Poland or Eastern European countries, all my grandparents came from Russia, was made from potatoes. Most vodka is made from grain, and potato vodka is much smoother than grain vodka, even though there's some really great grain vodkas like Grey Goose, Absolute, or Costco's French vodka, which is really almost identical to Grey Goose. And if you're in the Netherlands, Kettle One, which used to be called Neue Geneva, back when I went to the Netherlands and the exchange rate of the dollar to the guilder, they didn't have euros back then, was 4 guilders to dollar. I could buy liter bottles of vodka, then called Neue Geneva, for about 5 guilders or 10 guilders, which was $1 or $2 American. I brought a lot home on the plane. I was lucky. I always got it through customs. But anyways, that's one thing. The other thing is mainly the distillation. There's certain garbage that's, if you don't do a good distillation, that comes over when you purify the liquid. What comes over meaning you make a gas and it comes over and you condense it. And the very cheap vodkas, like Wolfschmidt and others, Dr. White knows his vodkas, has a lot of these impurities in it that give you headaches and a hangover. The best vodkas have never given me oh, you didn't hear that from me. Okay. Everything you want to know about liquor and vodka and you're afraid to ask, and that's chemistry too. All right, let's get back to solutions. Now, when we have a solution, there's an important concept. Now, I'm not a big rum person. I do like Canadian Club, which is not a rye whiskey, but Canadian Club. I like that better than Crown Royal, which is made by the same company, more expensive, but I like Canadian Club better. All right, let's move on or I'll get in trouble. Probably am already. All right, when we talk about solutions, there are two components of a solution. Solutions contain a solvent and solute, and somebody has a question option. And the solvent by definition, and by the way, time for Dr. White to get subtle. A solvent is the component in the solution that's present in the greatest amount. And then the other components are called the solute, or if there's more than one, solutes. And a solute is of a solution, is a solution component that is present in small amounts relative, or I should have even said smaller amounts relative to the amount of solvent. So you should know a solvent is the component in a solution that's present in the greatest amount. And all the other components, which are present in smaller amounts, are called the solute or solutes. All right, let me decode this for all of you. If you have a mixture of 200 grams ethanol, keeping to what we were just talking about, remember vodka is mainly ethanol and water, and 500 grams of water, then what is the solvent of that mixture? I could have written down, and what is the solute? 2 points each. Well, how do you do that? Well, the solvent is the component of the mixture present in the greatest amount. I hope you all agree 500 is greater than 200. So the solvent is water. What is the solute? And that's ethanol. Oh, this is fun. Let's do another one. Anybody need more time writing this down? That's your turn. If you have a mixture of 800 grams nitrogen, 200 grams of oxygen, I could have also written homogeneous mixture, then what is, ooh, I got double is. What is the solvent of this mixture? What is the solute of this mixture? Your turn. All right, I think everybody's done. Let's do it. What's the solvent? That's the component of the mixture present in the greatest amount, and that's nitrogen. 800 is greater than 200. And the other component is oxygen. And if you think about it, in air, which is an 80-20 mixture of nitrogen and oxygen, what's the solvent in air? Nitrogen. What's the solute in air? Oxygen. Oh, let's do one more. And let's do another one. If a mixture has 200 grams of water and 400 grams of sugar, then what is the solvent of the mixture? What is the solute of the mixture? Your turn. All right, looks like everybody's done. So I'm going to do this. Now, what is the solvent? That's the component of a mixture present in the greatest amount. I think you all agree 400 is greater than 200. So the solvent in this case is sugar. And what's the solute or solutes is the other component. In this case, the solute is water. Now, most of you probably know in our life, water is one of the most important solvents, but it doesn't always have to be a solvent in a mixture. And if I look at the clock, oh no, time flies when you're having fun with PV equal nRT and solutions and Dr. White and other stuff too. So with that, I'm going to remind you, don't forget, I'm now instituting a hard deadline in labs. Get the lab that's due this week in by at the latest Sunday. It should be really tomorrow if you have lab on Thursday or Friday. For those of you, if I don't see you Thursday or Friday, I should, but I'll remind you, have a happy Passover, have a happy Easter, or if you don't have any of those, have a happy spring break. In about 15, 20 minutes, I'll be sending out the email for test number 2. Please take it, make sure you get it uploaded with your answers by 1 tomorrow, 1 p.m. And I'll stick around a couple minutes longer to answer any questions if anybody needs a little help. And with that, I'll do my world famous goodbye. Goodbye. No, you know the goodbye. Gang gesund, be healthy. Bye. You can run away now.